Okay, so this is about work in progress for the last 30 years. So, I won't have any concrete results. I'll just be describing some ideas. And I was feeling like I was making some progress when I heard about this trip to Norway. And there's been a lot of distractions since then. So that's the reason for the incoherent discussion that may follow. Who knows? Okay. So, okay, where is the eraser thing? It's gone. Oh, there it is. Not anything intrinsic. So, first, just to there is this ODE in an infinite dimensional space of vector fields on 3 space, and I'm thinking of triply periodic 3 space, so it's really compact. And then, since you have a Riemannian metric, just a flat metric, then a vector field can be thought of as a covector field, just identifying the tangent space and the cotangent space. Vector field is a cross-section of the tangent bundle. So cross-section of the cotangent bundle is called a covector field, or one form. And one forms form this nice algebra with the exterior product, and you have the exterior differential. Well, they generate an algebra, with the functions, all the differential forms, and then you have this nice algebra structure with the wedge product, and you have the exterior differential, and you also have the star operator that takes an exterior, a k-plane, and goes to an n minus k-plane with an orientation. And so you have these various structures, say eta is a 1 form, and then omega is a 2 form, and I don't know, capital omega maybe is a 3 form, and f is a function. Those are the usual notations. So let's see, we have f is a 0 form, eta is a 1 form, omega is a 2 form, and say capital omega is a 3 form, a volume form. Okay. And I have to say this because we have such a mixed audience here. This is the sort of thing that would not be known here necessarily, but I learned this from John Morgan. So this is not part of my talk, but I want to say it anyway. So in vector calculus, you have functions, and then what can you do to a function?
Multiply.
What?
Multiply and differentiate.
You can multiply and differentiate, but say it you can form the gradient up. Like in Norway, they say, you ask, where is blah, blah, blah? And they say, go up. That means you follow the gradient and you get to so-and-so, if that's the answer, right? Anyway, so you have vector fields, and you have this gradient function, gradient operator, and then what can you do to a vector field in 3 space? That's a symbol. Give me a word. I'm a topologist. Huh?
Curl.
Curl, right. So we can do the curl. That gives another vector field. Sorry, that's not written right. And then what can you do to, another thing you can do to a vector field? Divergence, right. And that goes to a function, right? Now, do you guys know the name John Morgan? He's a topologist and analyst, but this guy really understands things. When the Perelman proved the Poincare conjecture, we waited for Morgan to write the book about it until we could be sure it was true, right? I mean, really true, because there's a long proof. Anyway, so he understands things very clearly. So he told me, Dennis, you know, this can be related to the following things. So let's call these omega 0 forms. This is omega 1. Omega 2 and omega 3. So let's write that down here. Omega 0, omega 1, omega 2, and omega 3. So these are the differential forms of de Rham theorem, de Rham's theory. Now we have this wonderful thing, the exterior differential. given by Poincare, D. D goes from D of a 1 form is a 2 form, and D is a 2 form is a 3 form. Now, I feel like, what is the sort of categorical difference between this discussion here and this discussion here? This is the sort of thing that topologists worry about, and analysts and people who compute don't worry about, okay? But for us, it's very important. This discussion here only uses the smooth structure. And if you have two different regions where you're doing this, and you have any smooth map from here to here, you can pull everything back, and it's consistent with the discussion here, right? This discussion here, however, uses the metric. And for example, vector fields, just by themselves, you can't pull them back by a map. You know, even though with the metric, vector fields and one forms are the same, you can pull back one forms by any map, but you can't pull back a vector field. Because a vector, why? Categorically. This is like testing.
No connection.
What?
There's no connection.
Well, no. What do you mean there's no connection? How could you pull it back if you had a connection?
Well, then I can go from one function space to the other, define the derivative of the.
I don't think you can pull it back even if you have a connection. If you even have a metric, how do you pull it back? Why? Huh?
You can push forward vector fields and pull back the forms, yes?
No. Wrong. Wrong. A vector field is an infinitesimal automorphism of the compact manifold. You can integrate it to get a flow. So it's an isomorphism. If you have two objects in a category, you have an automorphism here and a morphism between them. You can't pull back a morphism, an isomorphism, only if this is an isomorphism, right? It's just fundamentally no. It's an infinitesimal automorphism. It's not an endomorphism. But anyway, even if it were, it couldn't pull it back. Okay, so the objects in this row here are very functorial. They don't use a metric to define. The objects here, which are very intuitive, gradient measures the change, curl represents some kind of twisting, divergence represents volume distortion. They're very meaningful, but they depend on the geometry being present, right? And they, as objects, they're completely different in terms of structure. Like a vector field is not like a one form, but they're isomorphic given a metric. Okay. So in fact, you could, well, this is equality. Functions are equal to zero forms by definition. And given a metric, a function can be multiplied by the volume form of the metric, and you get a 3 form, and all 3 forms are given that way. So these are isomorphic given the metric. And vector fields are isomorphic to 1 forms, and vector fields are also isomorphic to 2 forms because the star operator connects 1 forms and 2 operators, the perpendicular operator, right? So these are also isomorphic. I could have kissed Morgan when he told me this. He said, this diagram commutes. So these two things are the same. So I just said they were different, but they're actually isomorphic. This structure, all these things. So then I didn't have to, and now we have this great thing in topology that this is Poincare. He defined this and then proved this, like just with indices, right? D squared is 0, right? So now this is like a gift to you. If you don't know, if you don't have these equations memorized, you see, oh, if you first do the gradient and then do the curl, you get 0. Namely, curl of grad is 0. That's one of the identities. You don't have to remember it anymore. it means d squared is 0. And the divergence of the curl is 0. And then if you do divergence of the gradient, that's not 0. You remember what that is? Huh? What? What? I can't hear. Laplacian, right. So the thing that isn't 0 is this thing that we all know. So there's a huge amount of information in this diagram, okay?
Just remark that you
Huh?
go to the Algebraic and see a 3-minute movie about you, and then you would say that this is your favorite formula.
Yeah, this is, I want this great engraved on my tombstone. I hereby, anyway, I love this actually, And this sort of special about 3-space. I mean, there's analogs in higher dimensions, but it's sort of wonderfully perfect in 3-space. Okay, so that was extemporaneous because I'm not prepared, so. Okay. What happened? Oh.
There's auto deselect on the eraser, so if you...
Oh, it automatically does it?
I can turn it off if you want. Okay, now it works like what you're used to in real life.
I remember once I was talking to Galavotti.
Save the woods by this.
What?
You are not saving the woods by this. You could get a new paper.
Okay. I was once talking to a physicist, and I was trying to explain the difference between grad f and df, and he couldn't. There was no difference because the formulas are the same. Partial respect to x, partial respect to y, partial respect to z. Those are the components of the gradient. They're also the components of df. What's the difference? Well, to a topologist, they're completely different because df doesn't depend on the metric. I'm repeating again, and the gradient f does, and they have completely different functorial properties. So anyway, let's get back to the problem. So been thinking about this incompressible Navier-Stokes problem in 3 dimensions to sort of try to understand that equation. So I'll just write it down. So it says x is let x stand for a vector field, then the infinite instantaneous velocity of the fluid, but let's don't write it as x, let's write it as a 1 form. Using the metric. We have a metric, so we can think of the vector field as a 1 form, okay? And then we this thing where you take perpendicular, I'll call that the star operator. So there's the nonlinear term, which is eta wedge star d eta. Then there's and then you can add viscosity term in the Laplacian, but I'm not going to talk about that today. That's a linear term, and it helps. So we'll save it for the end run. And then this term is just there you want to work with incompressible vector fields. So this is a condition on eta. The divergence of the vector field should be 0. This term does not have divergence 0. So you take its divergence and then you find a term, find a function p so that this is essentially the gradient. Divergence of the gradient, i.e. the Laplacian, is given by the divergence of this expression with a minus sign. And then you put that term in. It's unique up to a constant. It's a Poisson problem to solve it. And so, sorry, dp. So for the moment, I'll just suppress that term. It's a function of this term. It's a linear operator applied to this term, essentially. Laplacian inverse of the divergence of this term. So you have 2 derivatives one in here. Divergence is another derivative. Plossian inverse is a smoothing operator of order 2, and that'll tell you what this P is. Okay. Now, you lose a little bit of ground because of this product here. Because whatever Sobolev space you're in, you would, if you didn't have that product, you would be staying in the same Sobolev space. But you lose a little ground, and that's the problem. That's in a nutshell. That as this thing evolves, you're losing ground, and then you could find out very quickly that this is the problem. And so they don't know in 3 dimensions, they don't know whether this process develops singularities in finite time or not. Even with this helping term, the Laplacian term, it's not known. Okay. So anyway, so that's like the problem. And then, so here, now topologists love the etas, the d's, and the wedge. They love this part because we have this in topology. In fact, since Poincare, I mean, these etas are integrands. Like you integrate eta over a curve and you get some number. It's some measurement along the curve. And the omegas you'd integrate over surfaces. And the capital omegas you would integrate over volumes to get volume. And then there's Stokes' theorem, and then Poincare started putting these arcs and surfaces under the integral signs, and then he sort of dropped the integration part and just said, look at these pieces that you're integrating over. They have, the two-dimensional pieces have boundary. If you integrate an omega over this, I mean, if you integrate something, an eta over the boundary, that is the integral of d eta over the interior. That's Stokes' theorem. Anyway, so you could, that's just a linear dual of the geometric idea of considering one-dimensional things, two-dimensional things, taking their boundary. So the boundary of this square is this thing here, and the boundary of this is these two things here. The boundary of the boundary is 0 because it sort of appears like this, and then these cancel. And then this sort of started what was called algebraic topology, where you just take pieces, blocks that live in the space, and you look combinatorially at what's going on. And so it's very natural to try to discretize this infinite dimensional ODE if we have these symbols here, interpreted discretely. Well, Poincare did that already. Okay, so let's discretize this equation, make algorithms, try to make nice algorithms. Of course, this is done all the time. There's a big industry doing this. But let's now use, the idea is to use the fact that topologists independently of PDEs and this problem have been studying things since Poincare, in the 1900. There's quite a vast set of ideas, and just that last point I was showing that John Morgan showed me, so you see how div, grad, and curl become all organized just in terms of an exterior D, and which has better functorial properties. So it's an improved understanding of what's going on. And then Poincare says that, well, this part sort of has a discretization. They're called cochains, linear functions on pieces. So what are these integrals? If you had a form and you integrated, the linear functions on this, and then the dual of the D becomes the boundary of the chains. So you have the boundary operator, and the dual is, we usually call it delta in topology, but it's a discrete form of this, and the function on chains is a discrete form of this, the cochain. So we have cochains, and we really have the things under the integral sign, which are the chains, and we have the boundary operator here, and then we have the formal dual, Hom dual, which is the boundary operator on cochains, and we have Stokes' theorem that relates the continuum to the discrete. But, you know, like when I was a grad student learning all this stuff, Adams, who was like the #1 at the time algebraic topologist for the hardest problems available, wrote a book, Student's Guide to Algebraic Topology. He didn't even put in the continuum at all, didn't put in Durham's theorem. And he didn't put in the fundamental group either, because, well, that doesn't matter, but there were other issues that were being discussed, and they were related to this symbol here. And this goes back to what Steenrod did. So I'm not giving my talk at all. I'm not getting to the talk, but this is talking about getting to the talk, so to speak. Okay. So actually back in the 30s, in fact, they didn't really have cochains and so everyone's heard this word cohomology. What the heck is it? Poincare only had homology, cycles that are probing the space, going around holes and missing parts of the space or enclosing things like this. They had cycles and boundary and these geometric objects, and he defined the Betti numbers and the torsion coefficients and proved something called Poincare duality. And it didn't really have cohomology. It was only in the 30s that Whitney and in Russia, actually Kolmogorov and Alexandrov also defined cochains and cohomology. And one of the nice things it had a product. So this was all discussed in the 1935 International Congress on Topology in Moscow. 3 groups came and presented their versions of cohomology. Homology goes back to 1900 in the boundary operator. So this dual theory of cohomology has a product, and it is the discrete form of this term here. So we have the discrete form of this term, we have the discrete form of this term in terms of this picture I was just describing with Poincare, and then 30 years later we have the discrete form of this piece. Also, well, okay, I'm trying to say two things at once here. Also, well, no, not also. Steenrod, well, these guys invented, Whitney invented this discrete form of a product, which is the discrete form of the wedge. In fact, if you take the combinatorial discussion of Whitney, and in his book called Geometric Integration, he discusses this, and you start subdividing, he has simple axioms on the shapes of the pieces, that they sort of stay bounded in shape and combinatorially bounded as you go down. Then nice things happen in the limit. Any version of this combinatorial product of Whitney will actually converge to the wedge, as long as you have these bounds and you subdivide. So this ring structure, this algebra structure, which you were emphasizing, emerges always correctly. And these 2 guys emerge by definition somehow. That's Stokes' theorem. So this structure emerges from any reasonable discretization that is used in algebraic topology. And now, interestingly enough, of the discrete level, here you have to use real numbers. At the discrete level, you can use integers. The integer valued cochains have meaning, and they define the integral cohomology, which has torsion information, which you don't get from the de Rham theory. And the torsion information, cohomology. Anyway, forget the cohomology, because we have to stay at the geometric level. There's an integer version of this. And then Steenrod in 1947, and there's also a nice associative version defined by, it's called the Whitney-Alexander version. And there's another associative one that works nicely for cubes. But anyway, there are nice associative versions, but they're very non-commutative. So this discrete thing, and I'm always curious about this, and I've never really made it into concrete math, but I'm 80% of the way there, which isn't fast enough. Anyway, that's just like quantum theory. Quantum theory, classical theory is everything varies continuously, the black body radiation and all that, and it's incorrect until Planck fixed it by discretizing, and then Heisenberg found the uncertainty principle, which is non-commutativity, right? Hey, algebraic topology already has those things immediately. And Steenrod showed that any formula for this discrete version of the wedge wants to be commutative. So in fact, when you break your space up into pieces and write this formula down, turns out when you switch A and B to BA, AB minus BA, you can actually deform locally one expression into the other. And then any two deformations are actually equivalent by a deformation of a deformation, and et cetera. He made an infinite hierarchy, and then he did some magic with the flip of coordinates and came up with what are called the Steenrod operations. These are extra structure inside the algebraic topology that are only there because you're working over the integers. And it works at every prime and stuff like that. So there's a lot, this is just the tip of the iceberg, the Stokes theorem stuff and the periods. There's a lot more stuff under there, and it's buried into this product. And I was sort of thinking when I heard about this problem in the 90s that they don't know about this, I started working on it, and then I saw that they lost ground because of this product here. It's where they lose a little Sobolev space, a little regularity, and then it'd be a lot easier if they didn't have that there, and then somehow we know about, at the discrete level, we know some things, a lot of things. This has kind of been what's been going on in algebraic topology since the 50s, actually. So, and then I said also, what was the also? Forgot, oh damn. Also, yeah. But, okay, it's definitely not commutative. However, the non-commutativity is sort of mostly obstructed because of the 2 and the flip. So if you introduced a half into the coefficients, you would sort of get rid of Steenrod's first obstructions. So you could make it commutative. You could just average the formula by AB plus BA divided by 2, and you would make it commutative. And then you could keep the product rule. So the axioms of Whitney are you could have it be associative over the integers, and you could have a boundary operator which satisfies the product rule, but it won't be commutative because of Steenrod. But you could say, well, I can average, because I could put a 2 in the denominator, and then I can keep the averaging will keep the product rule, and then it becomes commutative, but then it won't be associative. And there's a whole theory about correcting associativity by homotopies, which leads you directly into the free cumulants that were discussed in the last talk. The combinatorics of the hierarchy of corrections you need is isomorphic to one of the 3 cumulant discussions, according to Nissim Renaud, who was a former student of mine. So she has a thesis which you can look up, and you can see the connection. She'll even use the language of the previous talk. Anyway, so there's a hint of all that algebraic structure in this business too. So this is just trying to understand, so all this is understanding about how you would discretize the underlying structure of this equation. Don't just take the equation and write it out in coordinates and then just discretize it, but try to do it conceptually. That's the idea here. So try to do it conceptually and then see what you can understand. Okay, so let me go on. Okay, so I've got, let me put it back up here, D, wedge, I've got, and the forms. F, eta, omega. These are my players, you might say, in the continuum where we can write the equation and think about it. But these are the elements there. And now we see we can go to the discrete level and use the co-boundary operator, which is just the dual of the algebraic dual of the boundary operator on these pieces. And then we have the cup product. Did I write it that way? No, I wrote it that way before. There's a reason for doing that. It's really denoted by this. And then, okay, so this is like that. That's the discrete form. But there's a lot of extra structure here. See, we can't pass, see, in topology, one passes to homology and cohomology, and then everything becomes commutative and associative. You don't see all this structure. But topologists who are working on the ground, you might say, or in the trenches, no, you never take cohomology. You have to think at the geometric level of the actual representatives, and the reality is there. So, and that fits with the idea of what is the reality of the discretizations of this continuum model. Okay, so okay, these are the elements, and then okay, but then we want to discretize, and we're going to consider all kinds of pieces in space that are controlled somehow, discretize them, and then we have linear combinations of these and so on, and we have these operators, we have this cup product. And now, what about star? Well, Poincare told us about star, and you've probably all seen this picture. I'm going to, just for simplicity, I'm going to draw a triangulation. So this is like, you decompose space into pieces like this, and then Poincare said, you should look at this dual picture that you've all seen. So you put a point in the middle of each top dimensional piece, and then for each wall you connect lines across the wall, and then for each codimension 2 thing you have a transversal codimension 2 thing, and dimension 2 is just that open thing there. And anyway, we put that in, and then what we learn in topology, and this is only learned in the 60s and 70s, is that if you consider this joint pair of decompositions, which are Poincare dual, and then just throw away the picture and just think of them combinatorially, how they're interrelated, what's next to what in each case, and what sits over what, you can reconstruct the manifold from that algebraic information in all dimensions except possibly 4. It's still not quite finished in dimension 4. But the information of a manifold or space is in Poincare's picture and his dual picture, but combined. So somehow one's half, and usually in computer science, and they usually work with grids, that's not enough. Grids are not enough. Cubes are not enough. You have to, even in the line, when you just do that, it's not enough. I mean, even though there's only one line, but it's very important to have these pieces as well. And in higher dimensions, we sort of know that the analog of this in higher dimensions contains the combinatorial information of that in the derived sense, namely up to equivalence and the natural notion of equivalence and all that. The derived package contains the information to reconstruct the manifold. And this was product of, Milner, Browder, Novikov in the 60s, et cetera, and so on. So, except in dimension 4, it's not finished yet. But in all other dimensions, this is now known. Okay, so we want to have at least 2 layers, and in dimension 3, the specific one I work with has 8 layers, because I have 2 in dimension 1, and then I tensor product that 3 times. So 2 times 2 times 2, I get 8 layers, and that's what I have to use. Okay, that's going to be the way to discretize, and I want to use these discrete analogs of this stuff. This stuff here allows me to write the equation, but I don't want to just discretize the equation. It's sort of like the king and the verifier and all that. I want to use the reasons why things behave a certain way rather than just copying it. So here's the reason that this is the reason that you're in a manifold. You have this decomposition. Your space has this property, if things start moving, they don't just suddenly hit a wall, it just keeps moving. That's what it means to be a manifold. So we have that. So in topology, we have this understanding. That's what I'm saying. So the idea is to discretize using all this understanding to guide us. Okay, now, so star is embodied in this picture. And then D and wedge are embodied in those other pictures. Okay, now, most of the people, the union of the knowledge, it doesn't want to go anymore. Oh, now it went. I wasn't using my fingers right. Okay. I'm already past the generation that can learn this. So, still living back in the 60s. Okay, so the idea of this talk is study this equation, which when you write it in this form, has all the elements of the geometry of space as viewed by a topologist. The ring of differential forms, it's a DGA, it has all this interesting information, but you do it over the integers, and then you break the symmetry of the continuum, and so it can be corrected in various ways, and and so on. So that's sort of the theme. Now, okay, so I was on a run there. Let's see. So, oh yeah, now there's one more idea, which is it's related to almost every talk I saw today is related to some thoughts. Every talk actually is related to some thoughts about this, but can't keep them. I don't know the right order to say, but so let's see. So now. Okay, right. So suppose you have at one level of scale. So now let's think about scales. There's another funny thing about this problem. Sorry, I'm to repeat myself from last week. This equation is kind of funny. I mean, the whole business of the calculus is kind of funny. F of x plus h minus f of x over h. Then you let h go to 0, and then we get this great thing, f prime, and it has all these wonderful identities, like all this stuff with calculus. But actually, there isn't any physics below Planck's scale. There's no physical theory. It's finite. Everything is really finite. And computers can go down to 4 or 5 in one dimension to 10 to the minus 4th or 10 to the minus 5th. If you cube that and start doing matrix problems, you fill up the capacity of Google. I mean, It's very easy. So you get, it's a long way above the Planck scale. So we'd sort of like to have finite understanding of this and prove theorems that the computations are effective at the reasonable scales. That's kind of a different way to view the problem in the spirit of this conference, rather than the problem the mathematicians do is like, when does this PDE have nice solutions? So there's sort of two kinds of problems here. So I'm sort of thinking I'd be happy to understand either one, but I kind of like the second one better, the one to kind of be practical about this, which means understand the theory of the discretization. So let's think about scales. This is something else due to Poincare again. Poincare. Because he showed that if you break the spaces up into pieces, that, I have to give this beautiful one-line proof of Poincare duality, which is, see, if you take every piece of, like the triangulation, there's the Poincare dual piece in the hexagonalization, which is the transversal piece. Like for this point in the hexagonal, this point in the triangulation, there's the dual hexagon. I'm doing dimension 2 now to explain duality. And so for this point, there's this dual hexagon. And for this edge in the triangulation, look at this edge in the triangulation, its boundary are these 2 points. The dual of these 2 points are these 2 hexagons, but that is the co-boundary of this edge, which is the dual of the edge I started with. Now, I started with this edge and took its boundary, and start with this edge, take its boundary, these 2 points, then dualize that to get these 2 hexagons. Let's say go back and go the other way, start with this edge, take its star, which is the dual, and then take the co-boundary of that, and you get the 2 hexagons. That's the proof of Poincare duality in all dimensions, all manifolds. It says computing homology with the triangles, or doing computations with the triangles, is the same as computing cohomology with the hexagons in the complementary dimension. That's the Poincare duality theorem. This picture just shows it. Everything. And it shows something much deeper. It's happening before you apply those fancy words, homology and cohomology. Okay. So the problem is get carried away with each point, and I don't know what the next point is. Oh, yeah, right. Right. Sorry, I see now. Now, wait a minute. You should say, wait a minute, you're using one decomposition to compute homology and the other decomposition to compute cohomology. Why do you get the cohomology of the space? Well, Poincare proved that if you consider one decomposition and a subdivision of it, they produce the same computation. You get the same homology from the coarse algorithm or from the fine algorithm. So subdivision, for example, these two, the hexagonalization and the triangulation, have a common subdivision, which are these little kites. See, look at these little kites here. 6 of these kites make a hexagon, and 3 of these kites make a triangle. So it's a subdivision. You can amalgamate the kites and get either the hexagons or the triangles. And Poincare proved that when you amalgamate or subdivide, you don't change the topological invariance that he was computing, right? So we know then that the cohomology computed with the hexagons is the same as the cohomology computed with the kites, which is the same as the cohomology computed with the triangles. And we know the homology computed with the triangles is the same as the homology of the kites, which is then the same as the homology of the hexagons. So that's the proof of Poincare duality, because there's a common subdivision. And by the way, if you work with this common subdivision in any manifold, turn off airplane node or use high-fi Axwist data. What should I say? Okay? I don't know what to say. And how do I get rid of this thing on the side here that came up? See, this is where. Now you know what our home life is like. Oh, just do that? Okay, thank you. You're getting your exercise today. Okay, so Poincare understood subdivide. Now, if we were using squares and a various size and cubes, we would have nice systems of subdivisions, and we could sort of think instead of this is kind of related to the third talk this morning, which was my first talk about all the special functions, Fourier series, and so on. Right? That's you, right? So. There's two ways to talk about scales. Physicists often talk about special function scales, cutting off the eigenfunctions, Hermite or whatever, cosines and so on. That's one way to cut off the scales. That was in your talk. Lambda, your big lambda. Yeah, you considered energy cutoff, the thresholds you called it, right? So you cut off. And that's one way to cut off the scales, right? I mean, but another way is what a poor topologist can do, which is just break the space up into little pieces and then break it into smaller pieces, like wavelets. The wavelets fits with that, right? So that's the way I'm going to think about it. This is already in Poincare because he was using it right now to show that the basic topological information doesn't change when you subdivide. That's kind of, right? And so actually all of these nonlinear structures in some sense don't change when you subdivide. On the other hand, when you look at the maps between them, well, there's this nice word crumbling, you know, it's an English word, you know, cookie crumbles. You know, if you have a cookie, if you want to share a cookie between 3 kids, or 4 kids, I don't know, you break it, right? And then, so what happens, there's a natural map. If you think of these pieces in the homology way, the hexagon crumbles into 6 little kites, right? If we're working at the scale described by hexagons, we could then, each hexagon would crumble into 6 kites, and each edge would crumble into 2 shorter pieces, right? So then the dual map on cochains is averaging. So you would have values on all the little kites. Then you could compute the value on a triangle by adding them up. Add up all the 3 little kites, like integration. So it's like averaging. So at the level of I'm going to talk about your side and my side, okay? I haven't said what my side. Your side is think of functions and Fourier series and integration and all that. Then when you go from one scale to the next, that's like an averaging process. And renormalization is often expressed that way, and like Wilson when he did his work. And then that was in the previous talk about cumulants. The average of a product is not the product of the averages unless they're independent, and then they are. So implicitly in this problem is that notion of independence too, because if things were independent, then this nonlinear structure would go nicely from one stage to the next, because you have to average. Okay. So then that's why this student of mine has all of these cumulants in her thesis, because she was studying how the nonlinear structure between scales is actually coherent from the point of view of topology. That there are all these cumulants that have to be dealt with, but they can be dealt with in a homologically meaningful way. So these are all chestnuts, you might say. Okay, these are all chestnuts. Okay, so how much time do I have left? 0? A small number. Okay, small number. Okay, fine. So I'll just edit. So I noticed just before I heard about I was coming to Norway that, wait a minute. And this is my favorite thing, actually. The reason this picture, my favorite thing since I was a graduate student, the reason this picture tells about a manifold is, oh, it's really too bad I have to almost zero. So, yeah, I gotta say a little bit about three space. Well, okay, no, okay. We have to think now in three space. So we have edges and we have two-dimensional things that might be transversal. So this is this thing here, you know, it's the edge is, I didn't draw it right. The edge goes in here and then dot, 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 it comes out the back. Okay. So this is the picture of two geometric objects intersecting transversally. And you also have the picture of two-dimensional things intersecting transversally. So, oh yeah, that's why I forgot to say this at the beginning. Oh, damn. Okay, so I'll try to round up now. So, yeah, okay, so so remember that nice thing that Morgan told. What we'd like to do is take this equation and take it apart in terms of structure. And I've been discussing these different elements of structure that are used in this equation. So I've been discussing that. And now it turns out there is something interesting you can do, which is related to this picture. So I'm going to write this down. This means the inner product of two, given the metric, I have the inner product of two vector fields or two one forms. There's a natural L2 inner product on one forms and K forms and so on. And then the inner products on everything. So I'm just going to refer to that as that. And now when we're studying this PDE, turns out this eta should be volume preserving. And I'm going to just quickly say that I'm going to discretize that. I'm going to think of it as a vector field, which is volume preserving. So by Poincare recurrence, it goes around. And I'm going to discretize that as a one cycle, which is a boundary. So it's not only a one chain, it has to be a cycle because that's the recurrence. And then I'm also going to assume it's a boundary. So I'm going to consider that. And then there's this wonderful thing, which is really cool, is that on these chains at any level of discrete, and you take the cycles that bound, you can define a linking number. So if a cycle bounds, you span it by something that shows that it is a witness for it being bounding. And then the other cycle, you see how many times it passes through that surface that bounds the first one. And then you have to understand how to correct it when it just glances by the boundary, but you can do that. And so there's a natural linking form on the cycles which bound. And I'm denoting that by this. So I'll call this the linking form. This is the metric. I just will have that. And then there's a third thing, which is a ternary form, which if you take this equation and put a test vector in and integrate through, it turns out the stars magically disappear. And this goes away. If you test with something orthogonal to it, it goes away. And then it turns out you get a triple form. And this, in the continuum case, is just the integral of eta wedge, I meant to say eta there, and then eta double prime wedge eta, say. So this integrated over the three manifold. Here's a natural triple form on my objects, and I'm going to restrict attention to the ones that correspond to bounding 1 cycles. Anyway, so I have this triple form. So it turns out, so this is called the triple intersection form. And intuitively what this means is really like you have 3 surfaces and you measure how they intersect transversally, and then with weights and add it all up, and that gives you this number. And this will be an alternating 3 form. And it's purely topological, that's the point. Triple intersection form. And this is the linking form. And this is the metric. And then it turns out this data determines this equation. So this I learned in the early 90s, the middle 90s. So this is another chestnut. So the point of this is purely topological. The linking form is purely topological. It doesn't use the metric. And this is purely topological. And then the metric is just there to optimize certain parts of the process. So this is a conceptual chestnut as well. This is a main chestnut, you might say. Okay. Then the nonlinearity is coming from this, can be expressed in terms of this triple form by hitting this equation with a test function, another variable, and then you sort of have this guy, and then the test guy. So you have 3 things when you integrate out, and integrating against the test guy is evaluating this triple form. What's that? Ah. Okay. So, now, here's the moment, okay, the latest chestnut, which is, see, if you think in his side, special functions and forms, Fourier series for the cutoff, you have to do this averaging, and then you get these cumulates, which is in the last talk, which gets pretty complicated, right? But if you think of it in terms of intersection, linking is like related to this picture. And triple intersection would be you would get first 2 things intersecting in a line, then you'd have a third piece coming through here. And if it were transversal, it would just intersect there, and you would count that triple intersection point. That would be the data that goes into that number that reads out here. So the nonlinearity, which makes the going from scales to fine scales to coarse scales, or vice versa, depending on whether you're in, what's your first name?
Elliot.
What?
Elliot. A-R-I-E-H.
Arlia? Arlia? Is that all right? Arlia. Which leads to cumulates because you're averaging, but if you look on the other side, it's intersection, then it turns out that, so here's let's look at this drawing here. Suppose we subdivide. We go to a finer scale. We may subdivide even like a lot. And then we subdivide this a lot. Okay, now notice all the intersection between all the pieces, the only thing that counts is this small little thing divided into 4 things, and then one little piece coming out and one little piece going on the back. In other words, the intersection is local. So when you subdivide in a way which is consistent with the triangulation, this is part of the decomposition, the knowledge of that intersection is still there when you subdivide. So in fact, you can build carefully systems of subdivisions going down as high as you want, so that these 2 structures, which are topological, are compatible as you go down. So So that doesn't mean that you have the system breaks down and so on, but it's a certain compatibility. So you can make algorithms which have a certain compatibility. And just the last thing I'll say is,
There must be something about.
no, it's my fault. Okay, I can't, I see, you'll just use one hand. Okay. Okay. And it's something like, so at one scale you have, I want to draw things, big things like you have, these are the big edges of a coarse scale moving along. And I wanted you to think of this. Think of a jungle gym. You know what that is? The one, you know, in child's playground, like the edges of a cube. But cubes together, then you take all the edges. Is that okay, a jungle gym? I'm not so sure. Anyway, let me draw a jungle gym. So let's, and then, no, I can draw it like this. Okay, and then you have the dual jungle gym. You put points there, and then you have an interlocking dual jungle gym. So you can see you have one jungle gym and then the other one, and they're disjoint, but they interlock. So somehow this picture is the basis of understanding what space is. If you just have all those pictures at every scale, you can reconstruct the space correctly from the point of view of topology. So interlocking jungle gyms going down. Okay, so now you can think that here's one big jungle gym and so on, and then you have, imagine you take a much smaller scale and you have another interlocking jungle gym. Then you're going to have all these little things here. And then as far as I've gotten so far, it turns out that the structure of the nonlinearity decouples between the two scales, except for the little ones that are kind of going around the big ones. And then, in other words, so in the interior here, in the space in the interior, all of the stuff that's happening in the nonlinearity and the structure of the fluid equation at discretized forms doesn't even interact cleanly with this. And here there's some small fraction of it is not wanting to uncouple. So in some statistical way, it seems to uncouple. Anyway, though that remains to be understood. And then the point is that and then given that picture, the point is that this cubic form here, which represents the nonlinearity in the equation here, fits nicely as you go down. There's a coherence, but the coherence, when you pass it to the equation, there's an extra term of not perfect coherence that has to do with how the little guys interact with the big guys. But this is a small fraction of the little guys. So that's where I'm at right now, okay? So the point is that in the dual of your picture, the cumulants don't enter. How? Okay, because of this, it's a geometric point. So there's some dual, so even in your story, there should be some dual analogy of every one of your discussions that has different flavors when you cut off. Well, that's a lesson to be learned here. Okay, I'm going to stop here. Okay.